Hello, everyone, and welcome to Going Serverless. Today we're going to be talking about different Go language design patterns for serverless deployments. And in order to talk about this topic, I basically want to have a story that we can work around. And our story is that we have the idea for an API that can basically take, any kind of, data object, store it, generate a key for it. Then you can use that key to retrieve the object, delete the object. And by default, the object will have some amount of expiration. And you can think of this kind of like a Snapchat type of functionality. Given a piece of data, it'll only persist for some amount of time, and you can give a key to people to look at it. And because this is a brand new idea that we're not sure if it's going to succeed yet or not, we want to make sure it's cheap. So, given that this is what we're trying to build, why would we use serverless? And there's a few reasons for that. Most serverless is basically usage-based payment. So, sometimes it's compute time, sometimes it's, memory, in the case of AWS Lambda, it's memory in time. Sometimes it's just purely runtime. You also don't have to worry about managing your infrastructure, which means you don't have to worry about, patching a server, or, any kind of operating system updates. And then you also don't have to worry about scaling. Basically, because of the usage-based pricing, the cloud provider is going to handle the scaling for you. And usually the pricing doesn't change regardless of the scale. So that makes it good for when you're running under low load, you're not paying as much. When you're running at higher load, you're paying more. But hopefully at that point, you're also making more money, so that's okay. So then some notes on serverless, because there's a lot of things that can be serverless, and we're specifically talking about serverless compute. And in serverless compute, there's a couple of different general types of solutions. There's the container-based solutions, which is basically anything that will host a Docker image for you, and there's everything from ECS and Fargate, and then there's managed Kubernetes options like GKS and EKS. But what we're really going to be talking about is function-based solutions, and that's AWS Lambda, Google Cloud Functions, Azure Functions. And the distinguishing feature for functions is that instead of taking an entire Docker image, all you have is you actually have code or a binary with a very specific entry point for a very specific kind of invocation request object. And sometimes that can be a cron job, that can be an HTTP request. And we're going to be talking about HTTP-based functions. So we know what we want to build, and we can think about how we want to build it. So we know that we want to deploy our API as a serverless function because of all the benefits we talked about. And we also, as Gophers, we also know that we want to have clear and idiomatic Go code. And ideally, we also want our developer experience process to be as seamless as possible. So we want it to be very testable, and we want it to be easy to iterate on. Now, there's a couple major options that we have when it comes to picking out our stack. And specifically, I'm talking about AWS Lambda and Google Cloud Functions. Now, the reason I mentioned these as opposed to Azure, for example, is that these are the two that have a truly native Go support. In the case of Azure, you need to do some kind of funky wrapping of the Go code in order to be able to run it as a serverless function. Now, both of these cloud providers, AWS and Google Cloud Platform, they both have databases that we can use for API. In the case of AWS, it has S3, and in the case of Google Cloud Platform, it has its storage buckets. And both of these services also have lifecycle management policies that we can use to manage the time to live that we have on our objects. So that way, our code doesn't have to worry about expiring objects after a certain amount of time. We can just let our infrastructure worry about that. And for the sake of this talk, we're actually going to be focusing on Lambda. And the reason for that is that it's the most mature ecosystem in terms of Go support. And it's also been around, AWS has been around for so long that they have the largest market share. And we want to basically take advantage of everything that AWS already has to offer. That being said, we will look at we will talk about Google Cloud Functions later on in the talk. Now, as a bit of an aside, just to help those who are following along with the code understand, everything that we're going to be talking about here is real deployable code, and I'll have a link to that here in a minute. And all of this is deployed using infrastructure as code tools, specifically Pulumi. There's other tools you can use, Terraform being one of the main examples, or if you're being very AWS specific, there's CloudFormation. And what these tools let you do is basically declaratively describe your infrastructure, and it can reproducibly deploy that without you having to interact with any UIs or anything like that. And in general, it's considered to be a best practice whenever you're managing your infrastructure. So now, that being said, let's get started. And here's the link to the code that I was mentioning earlier, and I'll make sure to call out where we are currently in that repo as you follow along. So we're getting started. We at this point, let's just say we don't really know anything about AWS Lambda, and we just start building our API. So as we're about to write our code, we look through the through the documentation, and we find out that actually we can't use just a native Go HTTP request as what our function takes. And the reason for that is actually AWS Lambda needs to take JSON encodable objects, and because the standard library's HTTP request actually has unexported fields, it's not actually a serializable JSON object. But there's already there's already a library we can use for this provided by AWS called AWS Lambda Go, and it exposes an object that is what we will get from our API gateway proxy whenever our Lambda is invoked. And as you can see from the function signature, it doesn't look anything like a Golang HTTP handler func, right? We would be expecting an HTTP writer and an HTTP request object. Instead, we're getting this context, this API gateway proxy request object, and instead of having no return, we're actually returning the proxy response object and an error. So now that we have that, there's enough fields in that request object for us to basically do our own routing, since obviously we can't just use a standard Muxer or HTTP router. And what we can do is basically use this to sort of dictate the logic, when are we going to be writing an object, when are we going to be retrieving an object or deleting an object. And the nice thing about kind of doing this right up front is that it's actually going to give us a little bit of decoupling from that non-native Go object. So basically, if you look at this post file method that we were invoking in the last slide, you'll notice that we're actually just taking string data, and it doesn't actually know anything about API gateway proxy requests or API gateway proxy response. So it has decoupled that very AWS specific layer. So doing this, we can use unit tests to get a bit of coverage. We can effectively test say in this case test the helper to see that we can extract our keys correctly from the path. We can certainly test out our backend store. However, we are now kind of limited in how good our testing strategy is, because we've had to mock the input, and it's input that we have no control over. Unlike, for example, an HTTP request, which we could actually, we can actually do a curl, or in the case of Go, we can actually, usually we'd be maybe writing an HTTP test server and actually making HTTP calls from the the unit test code to that test server. So what can we do in order to get more confidence? Well, because it's serverless, an easy solution is to say, well, we can deploy. We can just deploy our application, and since we have the infrastructure as code tools, we can do this reproducibly. And they're actually fairly fast. We can, the first deployment took about a minute. Subsequent deployments took anywhere between 15 and 45 seconds. And, that's okay. However, the more and more we're deploying, and when you also add in compilation times, all of a sudden, like the development cycle time starts to add up, because it's not just, you can't just run your unit test from your IDE or from the command line. Now you actually have to go through a full deployment. So what can we do to maybe navigate around this? So one option is LocalStack, and LocalStack is basically an open source project that aims to provide basically API fakes, like locally running API fakes of different types of AWS services. And they actually have fakes for quite a few of them, everything from API Gateway, S3, Dynamo. I believe they have Kinesis as well. And one of the upsides is that theoretically, you can still use your infrastructure as code tools to deploy it. You're just going to have a different config that's going to basically override the different AWS API endpoints to point to your locally running local stack. But it has a few downsides. The APIs aren't guaranteed to be 100% compatible or up to date. Also, there's no IAM integration, which basically is, in terms of actually doing a full system test, is certainly one of the places where you might run into more issues. So it sort of falls short of what we want. It doesn't actually make our testing that much easier, and it also doesn't get us so close to testing a real world example where we greatly benefit from it, at least in my opinion. So if we're not going to use LocalStack, what can we do? So, instead of trying to figure out how, using different deployment tricks, what can we do from our code, right, from a language perspective, in order to make this a little bit easier? So, to start with, if you're actually following along with the code, you'll actually see that basically we started off with all of our files just effectively being in the root of our directory. Everything's in package main, which worked fine as we're just trying to get a proof of concept up and running. But so to start with, one thing we can do is use a kind of more idiomatic package structure. We can actually basically put our binary package mains under CMD. We can use internal package for shared libraries, and so on. Also, we a net HTTP package is basically the quintessential Go package. It's there's great examples for how to test it, for running, like I mentioned before, test servers that will basically host your Mux or HTTP router, and that way you can actually have real HTTP requests within your unit tests. You can also, finally, we can also basically abstract our store a little bit. Instead of worrying so much about it being an S3 bucket that we're talking to, we can basically use an adapter pattern so that we can either talk to an S3 bucket or maybe write these blobs to memory. So if we look at our original code layout, like I said, everything was just at the root of the directory. No real organization. But now for our new layout, like I mentioned, we now have that CMD package, which is where we have our binaries. Basically, each subfolder within that corresponds to a different Go binary. Then under internal, we have basically all of our shared common code, right? Toy is would actually host our server, has all of the server code. S3 store basically has the S3 implementation of our store, and the HTTP errors basically just helps us do some translation from AWS errors to a kind of idiomatic, or I shouldn't say idiomatic, but actually RFC compliant HTTP status translation. So like I mentioned before, we're using an adapter pattern here. And so this is what our server looks like now. And basically like the server struct, it just has an instance of store, it has the config that it knows about, and it has like a built-in router. And you can see that basically our store interface is the methods that we would expect given our API, right? Just get, set, and delete. And we have two different implementations of our store, right? Like I mentioned, we basically have like the in-memory implementation. We're protecting it with a mutex just because of any kind of like server is always going to be by default multi-threaded. And we also have our S3 implementation, right? So we can take advantage of this basically, and now we can see like when we start up our server, this is all very, just standard Go. We're specifically using the Go Chimuxer, but you could use any router or muxer that you like. But this is basically like starting any other server in Go, regardless of as if you weren't using any kind of cloud functions. So that now lets us actually set up test servers, and like I mentioned before, in our unit test. So here, like we're actually setting up the server. We're calling Go Start, which means it's actually being served on a port. And then then with this, we can run our tests, and as we can see, we're actually making HTTP post calls directly to our test server. So this is, this gives us a lot more. This gives us more confidence. Now we're actually exercising more of the entry point. And we can get a better sense of how like all the code is working together. But you might point out, this is now going back to just standard HTTP. This has nothing to do with AWS Lambda. And you'd be right. Everything that we're talking about so far is more idiomatic. It is, it's more like what you're accustomed to seeing when you're writing Go. But it doesn't actually solve our original problem. So what we have now is that what we can do is basically translate our API gateway objects into standard HTTP objects. And we can either do this ourselves, just write some helper functions to, say take the HTTP request body, read it all into memory and put it into the API gateway proxy request objects, its body field. But there's already like several of these translation libraries out there, and there's one that's actually official from AWS Labs. That's called AWS Lambda Go API Proxy. And so what we can do is we can take advantage of these libraries to basically build two different binaries. And what I mean by that is we basically, like as we already saw from our package layout, all the shared code is the same, but we're going to have two different entry points. One which is going to do the translation from HTTP to the API gateway specific objects, and another one that's just going to be like serving plain HTTP. And what this lets us do is lets us spin up a local binary that can actually host and receive commands locally. So we can basically, here I'm using HTTP pipe, but you could be doing this with curl as well. We're effectively invoking our API. We can test it out. We can, exercise edge cases, things that maybe we weren't ready to unit test yet. So this makes it a lot easier to test our business logic without having to fully deploy everything into AWS. And also, like we're basically using a makefile to kind of simplify the compilation process for us. You can see there's a build local target which lets us build a HTTP specific image or binary rather, and there's a build Lambda target that actually lets us that makes sure to cross compile the Go code into for Linux. You'd also have to specify AMD64 if you're if the computer that you're running this on isn't AMD64 architecture. And it zips it up and gets it all ready to be deployed. So, this is nice, but is there a way we can be a bit better? Because right now we're still, AWS specific. we've cleaned up a lot of the code, but we can certainly improve our abstractions a little bit. And basically, like, a lot of this comes down to taking advantage of prior art. And what I mean by that is take advantage of the fact that there's already libraries out there that do abstract, some of like these commonalities between different backends. In our case, we're going to talk about the Google Cloud Development Kit. And what that's going to let us do, or what it is to start with, the Google Cloud Development Kit is basically a library, or rather a set of libraries that's built by Google, presumably to make it as easy as possible to switch to their cloud if you want to. However, it does actually let you use different types of data sources if you're talking about blob storage. It has several abstractions for for things like queues or in-memory stores, and it's a very nice library that makes it easy to have some fairly portable code. Now, there are some drawbacks in that it can obviously, like, their common interfaces can't expose everything that the native AWS or GCP or Azure implementations of some of these things do. However, they do give you an as operator to basically get the types, get the AWS specific or Google specific types back, so you can do those operations if you need to. But that being said, there's already a blob library that's specifically for blob data storage, and this library already contains methods that are, in fact, kind of like the ones that we previously had for get, set, and delete. It basically already has a delete method, and that you can create a new reader or new writer for a certain file. And by doing this, we actually get to basically delete all of our previous store code, and all our server has to know now is that it's going to have Google Cloud Development Kit blob bucket blob bucket client, and that's all it has to interact with. So now we can update our unit test so that we can basically optionally either use file blob storage, just like stored in on our local machine. As you can see here, we just it opens the bucket, you give it some directory, and then we can just instantiate our server agnostically, just saying here use this store. And then we can also update our local binary actually to now, if we want to, not only run locally, but run so like we can serve our HTTP locally, but we can either use local in-memory or file-based storage, or we can use our S3 backend if we want to exercise some more of our path as we're testing things out. So one interesting thing about this is, like, even though we deleted all of our previous storage code, by bringing in the Google Cloud Development Kit, now we can actually support Google Cloud functions as well, not only AWS Lambda functions. And this is great. However, there is a catch, and the catch is that Google Cloud functions have different entry points than AWS Lambda. AWS Lambda expects your handler to be to fit certain different types of interfaces, accepting that JSON encodable object like we talked about, and expects all of this to be in package main. On the other hand, the way that Google Cloud functions work is that they actually have their own main, and they are they're treating your code as a library. So because of that, what you actually have to do is you have to have your code in a non-main package, and you have to basically expose a very specific signature. The upside is that the signature at least is standard Go. However, the fact that it's not coming in through main means that we can no longer structure our code the same way. That being said, we can kind of get around this using a little makefile trickery, and we can basically actually, we can actually grab all the files that we need to and move them into the right package structure, and then once we have that, we can upload it to Google Cloud Platform, and it will work. And as you can see here, once again, I'm using HTTP to basically run tests from my local machine, using my the Pulumi stack code here is all it's doing is getting the name of the invocation URL for my specific function, and we can run this and test locally from our machine, or even give it to our users to use. So now we basically were able to, now we could deploy it locally, we can deploy to AWS Lambda, and we can deploy to Google Cloud Functions with less code than we had in the previous phase. So that's great. Again, there are some places where, depending on what your project needs, these kind of abstractions may not always work. But I would say that there's quite a bit of functionality within the Google Cloud Development Kit or other abstraction libraries. And in general, I would encourage you to try to think about how you can abstract your code, whether it's using adapter patterns or using libraries like this to help you be flexible where you can be. There's always going to be situations in which you need very, very specific functionality from a specific type of database or a specific cloud provider. And in those cases, you may not be able to get that kind of abstraction. But if you can, it can make you a lot more flexible with your testing strategy or deployment strategy. So all this being said, do we have any other options? Are there any other ways that we could go about achieving the same end goal? Well, there actually are. We've our code's already pretty good. It's flexible and all those things, but we can actually consider basically the options that we get from build tags, which is usually a cross compilation tactic that gets used more often than not when building kind of the either embedded code for embedded systems or very different architectures. You'll see it a lot for the standard library when the underlying functions for say an HTTP or something like that have to work a little bit differently. And what build tags are is basically a line that goes to the top of a Go file above your package declaration, and you're basically giving it one or more tags in order to say when you're cross-compiling for this tag, include this file. And so in this example, this is again from our code, you'll see that we're specifically saying build AWS. So that means that this file will not be included during compilation if we're not specifying build AWS. And actually going back, we can see here that the compilation command in our make file is saying go build -tags AWS. So, and this is, I wouldn't say that this is any better or worse than our previous solution of using the different CMD directories in order to get a build. But this does have some advantages, and the advantages are that you get to basically reuse a bit more code in main. Obviously, previously, both our entry points had to instantiate our server, instantiate a server, read environment variables in order to configure the server, initialize it, and we can actually now keep all that in common in the same main, and we can actually use different serve files, so serve_AWS, serve_local, or serve_HTTP, and we can use those files to basically change what specifically we do in that scenario. But again, it's no better or worse. It's just a different strategy that you can take. So anyways, to recap, when we started off, we basically were writing code that was slightly decoupled from API Gateway, but it was not hard to deploy, but it took a while to deploy, and that's a process that can get onerous and get tiresome if you're deploying a lot or iterating on your code a lot. So then, from there we moved to to more idiomatic package structure. We started using the AWS Lambda Go proxy code that let us basically abstract away the translation for between an AWS proxy Lambda request and HTTP request. And we also basically got all of our shared code, so the part, the business logic, the database logic, all that stuff. It's in separate shared packages. And what we did then is we used like those different CMD targets to compile different binaries. From there, we mixed in the Go Cloud Development Kit, and we basically got even more flexible, and we got to delete some of our own code that we already had. Basically, we got to delete our own adapters, and that gave us the ability to deploy to even more different cloud providers. And finally, we looked at build tags, and the build tags, again, were basically taking advantage of the tool chain, the native Go tool chain, building different binaries, like leveraging tags. And overall, again, what I want to emphasize from this talk is that there's, serverless is really powerful. It gives us a lot of flexibility. But because it is a bit of a non-native solution, we definitely want to find ways to make the process of building, deploying, testing be as easy and seamless to the developer as possible. Anyways, thank you all for coming, and I look forward to answering your questions. Thank you.
Okay, Steven, thank you very much for the really interesting talk. And it's time for questions. We have at least question right now in the chat, and this is what kind of developer setup you are using to start on the local machine? SAM local, whatever SAM means, or other approach?
Yeah, so SAM is a technology that AWS has in order to. It's like a server application model. It's a very easy way to get started, like deploying, services into like a serverless stack into AWS. So what I actually used is basically like if you go look at the code, which I think was linked at the beginning of the talk, but it's under github.com/sbogacz/going serverless. You'll actually see that what I'm using is some infrastructure as code tools called like Pulumi, but then that's in terms of deploying all of the API gateway, Lambda, basically all of the AWS infrastructure. But in terms of locally, actually, when I originally wrote all this code, and that gave me the idea for the talk, was actually before SAM local even existed. So the local deployment is basically just hosting an HTTP server on an open port and like saving like everything either to disk or to memory, depending on which part of the talk we're talking about. So hopefully that answers the question.
Yes, thank you. Looks like you did. Another question is, do we have any other popular real cloud solution, serverless solution, other than Lambda and Google Cloud Functions?
Yeah, so Azure Functions are also pretty well developed. I wanted to expand the talk to include Azure, but it was going to take just a little bit too long, because one of the the same way that Google Cloud Functions and AWS Lambdas have different code entry points, the same thing happens with Azure, where basically the way that you actually have to run Azure is effectively having it's almost like having like a headless server constantly running, and then that real entry point is it's a shim that's going to be calling your headless server. So it's once again just like a little bit different from the other two options, but it also works well.
Okay. So for the tests, you are using S3 compatible, S3 replacement backed by a local directory. Is it easy enough to use the same technique for Google Cloud and Azure functions?
Yeah, I didn't get the chance to test it for Azure functions, but I think it should be equally as easy. And there's two adapters I use. There's the one I wrote myself, and I think it's in section 2 of the talk. And then there's also the one provided by the Google Cloud Development Kit. And the Google Cloud Development Kit one, if you go check out that project, you'll see that the options that they give you are really quite thorough. And there's also an option to basically typecast the adapter at again as the original blob storage. So if for some reason you needed a very S3 specific operation, you have a way of breaking out of the abstraction, doing the S3 specific code call that you need to make, and then going back to using the abstraction.
Thank you. Another question from the audience: how would the tracing requests and collecting metrics will be different in cloud?
That's a really good question. So there's, so actually in the context of AWS, they just came out with this notion of Lambda extensions, which is effectively also it's a layer outside. It's a layer outside of the running binary. So that can be a really good place to put in your instrumentation. But in terms of having a consistent method across, either Google Cloud Functions or alternatively AWS Lambda, what you can do is actually use open Census. And you can use both AWS's X-Ray and Google Cloud natively supports Open Census, and you can do that you can instrument your code with that, your actual server, to basically make sure you're passing through the context, and propagating the request ID through the code.
Yeah, makes sense. Okay, my personal question. To be honest, would you recommend serverless for pet project?
For a pet project, actually, yes. I mean, I've done it for several tests. I've actually for several personal small projects, and I've spent. I don't think my bill has ever been greater than $1 a month. So it's really cheap, which is really nice.
Yeah.
Yeah.
Okay. Continue, please.
Oh yeah, no. What I was going to say is that also it's. So at one point I did the math, and you would need to be serving at least if you have it configured to use I think 512 or 1 gigabyte of memory, on AWS Lambda, it would take 200 requests per second before it's cheaper to have the smallest server type that you can get. So basically, until you're getting 200 requests per second, and 200 requests per second is a decent amount of use. So for a lot of small projects, it's really cost effective.
So it looks like it is straight math you can do for your project and realize what will be cheaper and no other differences, right? It's what I've got from your talk. You can write serverless pretty easy.
Yeah, it's and the biggest difference is making sure you have a useful abstraction layer, because there are especially in the case of AWS Lambda, there are those AWS specific types, and again, ideally you don't want to be writing Go with types that you're not usually familiar with, right? So and that translation is actually pretty easy, right? Like we talk about in the beginning of the talk, it's not too hard, and I think if you take the time to make sure you have that translation, it actually makes the process of writing like your serverless code basically as easy as it is to write normal code.
Okay. Thank you very much. We have no more questions in text, but probably, and I hope, somebody are waiting for you in special chat. Could you please visit special chat, check if anybody is hiding there in the ambush? Thank you.
Thank you. Pas.